Okay, so let's see. Sodium channels are important for action potentials. They bring in all the sodium that depolarizes the cell, and those channels have two gates. One is called the activation gate, or the M gate, according to Hodgkin-Huxley 52, who named these gates and described them mathematically. So the activation gate opens because of the depolarization of the membrane. So a stimulus makes the membrane more positive, it depolarizes the membrane, and that opens the activation gate. When the activation gate opens, the cell depolarizes further because sodium comes into the cell. That leads to more opening of sodium channels because they're voltage gated. The activation gate opens, and that leads to more depolarization. That leads to a very sharp depolarization and to the peak of the action potential. Once we're at the peak of the action potential, another event occurs. That is the closing of the inactivation gate. So the inactivation gate is a second gate of the sodium channel. It's constantly open at negative membrane potentials, but it closes when the membrane depolarizes. So it's voltage gated. It closes when the peak of the action potential is achieved, and that effectively stops the inflow of sodium. At the same time, voltage-gated potassium channels are opening, and those voltage-gated potassium channels let potassium into the cell. And that opening of the potassium channels lets potassium flow out of the cell, suffusing along its concentration gradient. What that means is the inside gets more negative. And that means that now the membrane is hyperpolarizing, and is doing so very rapidly because there's no more sodium flow. Once that's done, we get into very negative membrane potentials. We're approaching the equilibrium potential for potassium, which is around -90. So we're more hyperpolarized than the resting potential of the cell. Since now the membrane is hyperpolarized, the voltage-gated potassium channels are closing, which means that now we're back at our resting state, and we're slowly returning to our resting membrane potential. Now, after the peak of the action potential, when the inactivation gate of the sodium channel closes, the channel becomes what we call inactivated. That means that no matter what you do, you cannot open the channel again. That's because the inactivation gate is slow, and even if there's a new depolarization that opens the activation gate, the inactivation gate can no longer open. That takes a few milliseconds, and in that period of time, the membrane is what we call refractory, meaning it can no longer generate action potentials. Now, as the inactivation gate reopens, or more and more channels that have been inactivated now get back to the state where the channel can be activated, it's getting more likely that you can elicit an action potential, and this is called the relative refractory period, because now you can elicit an action potential, but only with a very strong stimulus. And again, after a few milliseconds or so, this whole thing is done, and what you have is sodium channels that are in the activatable state, meaning you can generate action potentials just as before. Oh, come on,